All right, today we are going to be talking about colligative properties. Our learning target is to summarize the quantitative and qualitative effects of colligative properties on a solution when a solute is added. And to hit those learning targets, our success criteria are to identify the colligative properties of a solution and to measure the change in boiling and or freezing point of a solvent when a solute is added. So first of all, we're going to talk about colligative properties. These are properties of a solution that depend on the concentration of the solute molecules or ions, but not on the identity of the solute. So basically, bottom line, we're going to have boiling points that go up. We're going to have freezing points that go down based on solutes dissolved in a liquid. One of the most common examples that we see around here, okay, if we get a lot of snow, which is solid water, correct? If we get snow, we salt our roads. The reason being that salt mixes in with the snow and causes the freezing point to go down. Thus, the snow melts and our roads aren't as slick. Okay? So what we are going to do is we are going to do some calculations to see how much the freezing point goes down or how much the boiling point goes up. Okay? And we're going to do so by using these two equations. So if you don't have those copied down in your notes, you need to get these two equations in your notes. These are the equations for the boiling point elevation and the freezing point depression. Now what we're going to do just to start things off, we're going to work two problems. So here is the first one. Go ahead and copy that one down in your notes, and then we will work it. The problem states, what is the boiling point of a solution that contains 30 grams of sucrose, which is C12H22O11, that is dissolved in 100 grams of water? Well, we're dealing with the boiling point, so my equation is going to be delta T of B is equal to I is Van Hoff's factor. And what Van Hoff's factor does is it measures the number of particles formed when a solute dissolves. Okay? So, if, just real quick, let's go over this. If I have sucrose right here, sucrose is covalently bonded. So it is a molecule. When it is dissolved in water, it only forms one particle. So anything that is molecularly bonded has one particle. So for this one, Van Hoff's factor is going to be 1. Now let's look at something like calcium chloride. When we did computer lab number 13 and 14, we knew that if we had calcium chloride as a solid and we dissolved that into water, that we were going to get calcium ions in the aqueous solution, and we were going to get 2 chlorine ions in the aqueous solution, correct? Now, in this particular case, Van Hoff's factor would be the number of those ions. So I would have 1 calcium ion and 2 chlorine ions. So Van Hoff's factor for calcium chloride is 3. Okay? So it's different if you have ionic bonding or molecular bonding. Now, in this particular case, we have molecular bonding. So my Van Hoff's factor is going to be 1 here. Getting back to my equation, Van Hoff's factor times the boiling point, boy, that's a terrible K, the boiling point constant times the little m, the molality of a solution. So if I have those three, I, K sub B, and the molality, I can calculate my change in the boiling point. So what I do, like I do in a lot of things here, folks, I just line up things over here to the side and say, okay, what do I have? What do I need? Delta T sub B. For this problem, that's what I'm trying to calculate. Well, I know Van Hoff's factor because I said right here, that is molecular. So Van Hoff's factor is going to be 1. K sub B. That is the boiling point constant, okay? We are dealing with what solvent here? We're dealing with water. So I have to come onto that chart I just gave you right here, and I need to find water. So I'm looking at this chart here, and I bring it down. Here is water, so my boiling point, my boiling point constant for water right there is 0.52, and my label is going to be degrees Celsius per molal. So I come back, and my K sub B is 0.52 degrees Celsius over the molality. The final thing I need to do is I need to calculate my molality. So I take my value that I have for my solute. My solute was the sucrose. And my value for the sucrose was 30 grams. So I take that 30.0 grams of C12H22O11, and I need to flux capacitor that to get my number of moles. Well, I know that 1 mole of C12H22O11 has a mass of 342.2992 grams of C12H22O11. So my grams cancel. I'm going to come up with a value, and I'm going to divide that one out. So let me grab my calculator. Okay. 30.0 divided by 342.2992, and that gives me a value of 0.8764 moles. Now, I don't want just the moles, I wanted the molality. So I know that molality, little m, is equal to my number of moles over my kilograms of my solvent. Well, in the problem, it told me that I had 100 or 1,000 grams. So how many kilograms is that? 1. So that's going to be 1 kilogram. So this is going to give me a value of 0.8764 lowercase m. So I now have my molality. I go back to my equation. Okay, my delta T of the boiling point is equal to my I, which was 1. My boiling point constant was 0.52 degrees Celsius over molal, times my molality, which was 0.8764 molal. When I did that, I get a cancel on my molals, so my change in my boiling point is going to be labeled in degrees Celsius. So I take my 1 times 0.52 times 0.8764, and I come up with a value of 0.0 0.0457 degrees Celsius. Now, ladies and gentlemen, I'm not done yet because that's my change in my boiling point. I go back to my chart here. What is the boiling point of water? Well, that's an easy one. We should know that. That's 100 degrees, okay? 100 degrees Celsius. So what I need to do is I need to take my 100 degrees Celsius and I need to add to that 0.04557 degrees Celsius, and I come up with a value of 100.04557 degrees Celsius. That, ladies and gentlemen, that is my new boiling point. Okay? Now notice I didn't sig fig this, because if I would go back to my original problem, my sig figs would be, there's 4, there's 3, it would be 3 sig figs. So if I 3 sig fig this, it's still going to be 100, and it's going to look like I didn't raise it. Now what will happen on WebAssign, they usually tell you something like round this number to 2 decimal places. So if I would have done this, I would have had 100.05. So they'll tell you on WebAssign where you need to round it to. Okay? Any questions on that? All right, here is our second example. Go ahead and write that example down, and then we will work it. The question states, what is the freezing point of a solution that contains 35 grams of aniline, which is C6H5NH2, that is dissolved in 500 grams of benzene? So just making a mental note here. My solute is the aniline. My solvent is the benzene. So when I'm looking at my chart for boiling point, freezing point, and the constants, I'm going to look for benzene this time, not water, because my solvent is benzene. So once again, I'm dealing with freezing point depression. So my change in the temperature of the freezing point is going to be Van Hoff's factor times the freezing point constant times the molality of the solution. As I said before, I like to just line everything up at the side. I'm calculating my freezing point change. Van Hoff's factor. I go back and I look right here. And I say, okay, is that ionic or covalent bonding? What do you think, people? It's covalent bonding. So this is molecular. So my Van Hoff's factor is going to be 1. My K of the freezing point. Now I go back to my chart. Here's my chart. I got to go back up because I'm looking for my freezing point depression of benzene. And I can see that this value is right there, 5.12. Now, ladies and gentlemen, here's a catch. Here's a catch. We call it the freezing point depression, don't we? So the freezing point is going down. So we put that value as a negative value. So it's negative 5.12 degrees Celsius per molal because it is going down. We left it positive for boiling point because it's going up. The final thing I need to find is my molality. So to find the molality, I'm going to take that 35 grams of the C6H5NH2, and I'm going to flux capacitor that to get my moles. I know that 1 mole of C6H5NH2 has a mass of 93.128 grams of C6H5NH2. So my grams will cancel, leaving me with moles. So I'm going to get moles of C6H5NH2. When I do my math, 35 divided by 93.128, I get a value of 0.378. Now, I don't want the moles. I'm trying to calculate the molality. So I need to divide this by the kilograms of the solvent. Well, it tells me in the problem that I have 500 grams. So 500 grams is equal to 0.500 kilograms. So when I do my math, I take my molarity, or my number of moles, and I divide it by 0.500, and I get a value of 0.7517, and that's little m. So now I have everything I need to calculate my change in the temperature of freezing point, my Van't Hoff's factor, my freezing point depression, constant, and then my molality. Once again, my molality cancels, so I'm going to have my value in degrees Celsius. So I'm going to take all those numbers, 1 times a negative 5.12 times a 0.7517, and I get a value of negative 3.848. Now, once again, I am not finished. I am not finished because this isn't my new freezing point. This is how much my freezing point decreased. So I need to go back to my chart, and I need to find my freezing point of benzene, which is 5.5. So I'm going to take 5.5, and I'm going to subtract from it 3.848. So that's going to give me 2, 5, 6, 1.652 degrees Celsius. That is going to be my new freezing point. My new freezing point.